1. The magic of manufacturing. Additive manufacturing represents a paradigm shift from traditional subtractive methods, offering unprecedented geometric complexity and material efficiency. We're moving beyond conventional manufacturing constraints into a realm where design is limited only by computational modeling. This technology fundamentally redefines the production lifecycle, enabling rapid prototyping and highly customized end-use parts. The core principle involves the successive addition of material, typically in layers, to construct a three-dimensional object directly from a digital file. This process minimizes waste and allows for the creation of internal structures impossible to achieve with milling or casting. We'll now examine the foundational technology that underpins this revolution, specifically fused deposition modeling.
2. The hot glue gun robot. The fused deposition modeling process, or FDM, is conceptually straightforward but technologically sophisticated, relying on precise thermal and kinematic control. We established the broader context of additive manufacturing, and now we focus on its most accessible form. The mechanism operates by heating a thermoplastic filament to its glass transition temperature, allowing it to be extruded through a fine nozzle. This molten material is then deposited onto a build platform in a predetermined path. Crucially, each deposited layer must fuse chemically and thermally with the preceding layer to ensure structural integrity in the final component. The precise control over temperature and deposition rate is paramount for achieving dimensional accuracy and mechanical performance. This physical process begins with a digital blueprint, which we must first acquire or generate.
Step 1. Find or make a model. The initiation of any additive manufacturing process requires a standardized digital representation of the object's geometry, which is typically encapsulated in an STL or OBJ file format. This prerequisite follows the conceptual understanding of the FDM mechanism. The STL format, derived from stereolithography, approximates the object's surface using a mesh of triangular facets, defining the outer shell without inherent information about color or texture. Conversely, the OBJ format offers a more comprehensive data structure, capable of storing texture maps and complex surface data. Engineers and designers utilize sophisticated CAD software, such as Fusion 360 or SolidWorks, to generate these models, ensuring adherence to design for additive manufacturing principles. Alternatively, vast repositories like Thingiverse provide pre-validated models, accelerating the design-to-print cycle. Once the model file is secured, the next critical step is preparing it for machine execution.
Step 2. The slicer. The slicer software serves as the essential computational intermediary, translating the static geometric data of the STL file into dynamic, machine-executable instructions known as G-code. Having obtained the digital model, we now focus on its preparation for physical realization. The slicing algorithm performs a complex geometric analysis, virtually sectioning the 3D model into discrete horizontal layers, typically between 0.1 and 0.3 mm in height. This process determines the toolpath, generating specific G-code commands that dictate the printer's movements, extrusion rates, and thermal parameters for each layer. Key parameters, such as infill density and support structure generation, are defined here, directly influencing the object's mechanical properties and material consumption. The resulting G-code file is the definitive set of instructions that governs the printer's electromechanical systems during the actual fabrication phase.
Step 3. The print. The final stage involves the physical execution of the G-code, where the printer's motion control system precisely coordinates movement across the three Cartesian axes, X, Y, and Z, to deposit the material. The G-code, generated by the slicer, now dictates the machine's behavior. The X and Y axes define the planar movement of the extrusion head, tracing the cross-sectional geometry of the current layer. Concurrently, the Z-axis increments vertically after the completion of each layer, establishing the build height and the layer-by-layer additive nature of the process. Thermal management is critical during this phase. The material must be maintained at a temperature that allows for flow and adhesion but cools rapidly enough to support the subsequent layer without deformation. Successful printing relies on the seamless integration of these kinematic and thermal controls. We must also consider the common pitfalls that can disrupt this delicate process.
Common mistakes to avoid. We have established the additive manufacturing process, but the transition from theory to successful execution often encounters specific technical hurdles. The most frequent cause of print failure stems from inadequate first-layer adhesion, a critical interface that determines the structural integrity of the entire object. This issue is fundamentally rooted in two parameters: improper bed leveling and poor surface preparation. Bed leveling ensures the nozzle maintains a consistent, micrometer-precise distance from the build plate across the entire plane. Poor adhesion, often manifesting as the spaghetti monster failure, results from insufficient surface energy between the polymer and the build plate, which can be mitigated by using appropriate bed materials or chemical adhesion aids. Furthermore, the thermal profile, specifically the nozzle and bed temperatures, must be precisely matched to the polymer's glass transition and melt temperatures to prevent warping or insufficient layer fusion. Mastering these variables is essential for reliable, high-fidelity part production. Let's now consolidate the entire workflow we have discussed.
Recap: the 3 essential steps. Having examined the common failure modes, we must now return to the core procedural sequence that defines the fuse deposition modeling workflow. The entire process is a 3-stage pipeline, beginning with the digital representation of the object. Stage 1 involves the acquisition or creation of a geometrically closed, manifold model, typically encoded in the STL or OBJ file format, which triangulates the object's surface geometry. Stage 2 is the computational transformation of this geometry into machine-executable instructions. Slicing software converts the model into G-code, a sequential list of Cartesian coordinates and machine commands that dictate the toolpath, extrusion rate, and thermal settings. Finally, Stage 3 is the physical realization, where the printer executes the G-code, depositing material layer by layer along the X, Y, and Z axes to construct the object additively. Understanding this structured progression is key to controlling the manufacturing outcome. We can now consider the broader implications of this technology. Start your maker journey. We have thoroughly analyzed the technical and procedural elements of fuse deposition modeling, providing a robust foundation for practical application. The knowledge of model preparation, G-code generation, and process execution now positions you to engage directly with the maker ecosystem. We encourage you to leverage established repositories like Thingiverse and Printables, which serve as vast libraries of validated STL files, accelerating the initial design phase. Furthermore, the immediate next step involves downloading and experimenting with slicing software like Cura to internalize the parameters that translate digital geometry into physical reality. This technology is not merely a tool for prototyping, it is a decentralized manufacturing paradigm. Your participation in this global community of innovators will contribute to the ongoing evolution of additive manufacturing techniques and applications.